We're getting so close to the end of the semester. Section 4.5 I've titled "and problems" as opposed to section 4.4 when I did "or problems." And in "or problems," at least the problems that we did in section 4.4, we did kind of one experiment, and we picked one card from a deck of cards. We rolled a single dice. In this section, we'll be doing "and problems," and in "and problems," we're going to be doing an experiment twice. Like picking two cards from a deck of cards, or rolling two dice, or selecting two numbers from a hat. So the big difference is the number of experiments, as opposed to doing just one card, one die, or one letter from a hat. We're going to be doing two, and we're going to be doing probabilities for this section just like we did last section. And there's a formula for these probabilities too. The formula is listed here. So in an "and" probability, if I want to find the probability of event A and event B happening, I just multiply the probabilities of each of the events. So let me scribble something down. In fact, I'll do just something on the next page to help you understand what this formula means, because it's a little generic in terms of the A and B don't really feel like the problems we've been doing. So I made up an experiment. And my experiment will be here. Two cards are selected with replacement from a deck of cards. Of course, this means I'm going to pick one card, put it back, and then pick a second card. So the with replacement part of this tells me that I'm picking a card, putting it back, and then picking a second card. So these are the two experiments. I'm picking a first card and then a second card, and I'm doing them in order, a first, then a second card. Now it says determine the probability that two queens will be selected. So the events here, event A and event B for these probability formula, event A is going to be selecting a queen on the first for the first card, and event B is going to be selecting a queen for the second card. So in this particular problem, I'm trying to find the probability of getting a queen for my first card and getting a queen for my second card. So in terms of this formula, the A and the B are getting a queen on my first and the queen on the second card. This formula says the probability of getting a queen on the first card and a queen on the second card is going to be equal to the probability of getting a queen for my first card times the probability of getting a queen for my second card. So in order to do this problem, because it's repeating in an experiment twice, I decided I was going to use the probability formula for "and" problems, which is the formula that we use when we're finding probabilities for doing an experiment twice. I took the A and the B out of the formula, and I made them fit the problem, and then I interpreted how the formula would work for this problem. Now I'm going to attack this. In order to attack this problem, I need to be able to compute both probabilities. Specifically, I need to be able to compute the probability of getting a queen when I pick one card from a deck of 52 cards. And I should know by now that when I do card probabilities, the numerator is the number of cards that have the desired outcome. The denominator is the number of cards I have to choose from. And for this first probability, the probability of getting a queen for my first card, the numerator is going to be 4 because there's 4 queens in a deck of cards. The denominator is going to be 52 because there's 52 cards in a deck of cards. Now I'm going to go and do my second probability, and I'm going to multiply the numbers together. So the first probability was the 4 and 52 because there's 4 queens in a deck of cards. Because of the word with replacement, the second probability, the denominator is not going to go down. I'm assuming I picked a queen on the first try, I put that queen back in, and for my second fraction, the denominator is still going to be 52. I'm still going to have all 52 cards to choose from. The numerator is still going to be the same number. It's the number of queens in a 52 deck card, which is going to be 4. So each of the probabilities is going to be a 4 and 52. The probability of getting a queen first and a queen second can be found by multiplying these two fractions together. And I wrote 1 and 69 here, and 1 and 169. Let me just do this on my calculator really quickly. So on this calculator that I've been using all semester, I could go parentheses 4 divided by 52, and then parentheses 4 divided by 52. That's a way to show 4 over 52 times 4 over 52. When I hit enter, I get 0.0059, and for the most part we've been doing probabilities as fractions, so if I just hit the math button and enter twice, I'll get that number 1 over 169. I have no idea why I took this decimal and made it into a percent, but that decimal, if I wanted a percent, the percent probability, this decimal is not a percent, it's not a fraction. To change a decimal into a percent, I move the decimal 2 to the right, and this is how I got the 0.59%. So it's not very likely. It's less than 1% chance. That's not 59%. There's less than a 1% chance, because 0.59 is less than 1, to get 2 queens if you're picking one card one after another and putting the first card back. So the answer that I wrote was 1 over 169. And that's kind of what we've been doing kind of consistently. When we are doing probabilities, we have a tendency to write answers as reduced fractions. Let me do another example. Basically the same question, but changing one key word, and that's going to change the whole answer, or something in the answer. Enough in the answer that it's not the same problem anymore. So 2 cards are selected without replacement from a deck of cards. In this section, I'm assuming that I'm not picking the 2 cards at the same time. I'm picking one, looking at it, and then going in and picking a second. And I'll tell you whether or not you're putting the card back when you're going to get the second card. In this particular problem, 2 cards are selected without replacement, which means one card is selected, I look at it, I throw it off to the side, I don't put it back in, so when I go to get my second card, that card's no longer in my deck, and there's one less card in my deck, and then I'm going to pick my second card. So now I'm going to determine the probability, the same probability, the probability that 2 queens are selected, so that the probability that a queen is selected first and a queen is selected second. And the probability formula tells me that the probability of getting a queen on your first card, followed by a queen for your second card, can be computed by multiplying the probability that I get a queen on the first card times the probability that I get a queen on the second card. Now, when I go to make fractions, the denominators aren't going to stay fixed like they did in the last problem. In the last problem that was with replacement as opposed to without replacement, both the fractions had a denominator of 52. This is without replacement. When I go to pick the first card, I'm picking from a standard deck of 52 cards. But I'm not putting the first card back, and when I go to pick the second card, I no longer have 52 cards to choose from. I'm assuming I'm taking one of the queens out of the deck, not putting it back. My second fraction is going to have a 51 in the denominator. For the numerators, for the first numerator, I haven't picked any cards from my deck. There's 4 queens in the deck. The probability for your first card to be a queen is 4 and 52 because there's 4 queens in the 52 cards in the deck. If I assume I get one of the queens for my first card and I don't put it back, not only do I only have 51 cards to choose from for my second queen, but there's only going to be 3 queens left because the queen, one of the queens was gone. The second fraction here should be 3 and 51. If I want to figure out what this probability is equal to, I'd multiply the fraction 4 and 52 times the fraction 3 and 51. Might have an extra parentheses there. And then I'm going to math enter this. I would say it's less likely, there's a 1 in 221 chance as opposed to a 1 in 169 chance to get 2 queens if you're not putting a queen back, because it's harder to get a queen on the second try when there's only 3 as opposed to 4 queens. There's less cards but less queens. And then all this work here is just exactly that. So this next sheet or two in my notes talk about independent and dependent events. Quite honestly, you can read through these sheets if you care to. You want to pause the video and read this. This isn't going to benefit you at all in terms of being able to do the problems. So I'm not even going to comment about them. You could read through them, but just really look at it lightly. This might be interesting if you're going higher in math and doing a lot with probability, but the concepts of independent and dependent events, that's not something that we probably need to muddy the waters with here. Let me just kind of jump into the problems now. So homework, all the homework questions have the same sort of vibe to them. There's a lot of card questions, so having a card sample space is going to be handy. So 2 cards for problems 1 through 10 are selected from a random deck of cards, 52 cards, without replacement. So the without replacement tells me the denominator is going to go down. I'm going to pick a card and not put it back. So I'll do my problem 2. And my problem 2 says, what is the probability if I pick 2 cards that the first card is black and the second card is black? The formula that we're using in this section would say this probability can be found by finding the probability of getting a black card first times the probability of getting a black card second. The denominators for each of my fractions are going to go down by 1. The first denominator is going to be 52 because the deck of cards has 52 cards. The second denominator, because it says without replacement, is going to go down by 1 because I'm not putting back the black card that I picked up on the first try. The numerator for my first fraction is just the number of black cards in my deck. And for the black cards, it's the clubs and spades that are black. There's 13 clubs and 13 spades in my deck of cards that count as the black cards. There's a total of 26 black cards. So the numerator of my first fraction is going to be 26 because there's 26 black cards in the deck of cards. I don't know which black card I'm going to get, but I do know that if I take a black card from my deck and I don't put it back, that the deck that started with 52 cards, 26 of them being black, if I remove 1 black card, not only do I have 1 less card, 51 cards left, I have 1 less black card. So the number of black cards that I'm going to have to choose from for my second probability is going to be 25 because I'm assuming this card was taken and it was black. So the second numerator is going to go down by 1 because the 26 black cards no longer are in my deck of cards. Not only do I have 1 less card, I have 1 less black card. Let me just multiply these fractions together. The 26 and 52 times 25 and 51. And reduce the fraction. The answer to my question 2, the probability is 25 and 102. Similarly, your problem 1, I'm pretty sure it's also equal to 25 and 102 because the work should be exactly the same because red cards aren't really probability-wise different than black cards. Let's look at 3 and 4. If you want to skip through watching this and just figure this out yourself, I have 4 and 663 for your answer. I'm going to do my probability, the probability that the first card is a queen and the second card is a 3. So I'm doing the probability that I get a queen first and a 3 second. And I know that's the same as getting a probability of a queen first times the probability of getting a 3 second. And each one of these probabilities is going to turn into a fraction. The denominators are going to go down by 1 because I'm not putting the card back. So for my first fraction, I'm going to find the probability of getting a queen from a deck of 52 cards. And in a deck of 52 cards, there's 4 queens. So when I go to do this problem, I have a standard deck of 52 cards. There's 4 queens in it, so the numerator of the first fraction is 4. I'm going to assume that one of the queens is taken away from the deck of cards. So now instead of having 52 cards, there's 51 cards. What's the probability of getting a 3 on a second try, assuming one of the queens is gone? Well, the denominator is 51 because I took a queen out and I didn't put it back. The numerator is the number of 3s that are left when you take a queen away, and there's 4 3s left when you take a queen out of a deck of cards. The second fraction is going to be 4 and 51. When I multiply these fractions together, 4 and 52 times 4 and 51, and then math, enter to reduce the fraction, I get the same answer that I wrote for your problem 3. So I think the answer here is going to be 4 and 663. Six is tricky, and I don't know that we deal with face cards for you. Well, you can do 5, I'll do 6. Face cards are jacks, queens, and kings because they have pictures of faces or people cards. Any other card doesn't have eyes on it in some sense. So I'm trying in problem 6 to find the probability of getting a face card first and a face card second. And I'll do that by finding the probability of getting a face card first times the probability of getting a face card second. And it's the same assumption that I'm not putting the card back. So I'm assuming the first card I pick is a face card. I don't put it back, so there's only 51 cards to choose from for the second card. For my first fraction, the numerator is going to be 12 because the face cards are jacks, queens, and kings. There's 4 jacks, 4 queens, and 4 kings. There's 12 face cards in a deck of cards. So for my first probability, it's going to be 12 and 52 because there's 12 face cards of the 52 cards. My second fraction is going to be 51 because I'm assuming I'm taking one of the face cards away. The numerator for the second fraction needs to be the number of face cards in the deck after you pull out one of the face cards. And because I'm assuming I pulled out one of the face cards, there's only 11 face cards to choose from for my second card. And this, as a probability, if I do 12 and 52 times 11 and 51, is going to be 11 and 221. Your problem 5 should be 1 and 221. Your answer should be. I'll let you do 7 and I won't do 8 because I think you can do this without me. So give 7 a go. For an answer, I have 13 and 51 written down. And I'll help you with 9 and I won't do 10. It's a little bit trickier. So I'm going to do number 9 on this sheet. So it wants me to find the probability that the first card is not a 7. So I'm going to get anything other than a 7 for my first card. And my second card is a 7. And I'm still assuming I'm not putting the card back that I picked first. So to do this probability, I need to find the probability of getting a card that's not a 7 first and then multiply that by the probability of getting a card that's a 7 second. And my fractions are going to have the denominators dropping by 1 because I'm assuming whatever card I pick first, I'm not going to get it for my second card. I'm not putting it back. So for the first one, I need to find the number of cards that are not 7s. A deck of cards has 52 cards. There's 4 7s, so if I take the 52 cards minus the 4 cards that are 7, that will tell me there's 48 cards that are not 7 in a deck of cards. So for the first fraction, the probability of getting a card that's not a 7, it would be the probability of getting one of the 48 cards that's not a 7 of the 52 cards. For my second fraction, I'm assuming I picked out one of the cards from the deck that's not a 7, so there's only 51 cards left. The numerator needs to be the number of 7s left in the deck of cards after I pull out a card that's not a 7. And because the first card that I assumed that I pulled out is not a 7, I still have all 4 7s left when I go to pull out my second card. So the second fraction should be 4 and 51. And if I don't have a math error on my answer key, this is supposed to come out to 16 and 221. Let me try this. It feels so small. So to do 48 divided by 52 times 4 and 51, and then math, enter, it's exactly 16 and 221. That's the first 10 problems. The next problems, 11 through 20, are again picking 2 cards one after another, picking a first card, then a second card. And it asks me to find probabilities assuming that we replace the first card. So the denominators aren't going to increment down by 1. I'm going to pick a card, look at it, put it back in, then pick a second card. So for problem 12, I'm trying to find the probability of getting a spade for my first card and a spade for my second card. And I know that's the same, or it can be computed by doing the probability of getting a spade first times the probability of getting a spade second. And for this group of problems, because I'm assuming that I'm replacing, the denominators are going to stay 52. For the first fraction, the numerator needs to be the number of spades in a deck of cards, a deck of 52 cards, and that's going to be 13. For my second fraction, I'm ignoring the first probability, and I'm picking a spade from a deck of 52 cards again. Both of the numerators are going to be 13, because for both probabilities, I'm picking from all 52 cards. I don't care that I picked a spade on the first or not when I do with replacement, because that spade that I picked out, it's not removed from the deck, it's put back into the deck when you do your second draw. So each of the fractions is going to have a 13 and 52. And if I reduce this, I get 1 and 16. If I did it on my calculator, you'd get 1 and 16. For your number 11, I think it's also 1 and 16. So for 13 and 14, let me just do 13 with you. So 13 is the probability that we get a 6 for the first card, 6 for the first card, and the second card is black. That can be found by doing the probability of getting a 6 first times the probability of getting a black second. Because I'm doing with replacement, so I'm assuming that I get a 6 for the first card, I put it back in, and I try to get a black card for my second card. When I go to do each of the numerators, I'm going to ignore the first card because it's put back in. The first numerator, the probability of getting a 6 is going to be 4 and 52 because a deck of cards has 4 6s. I'm assuming whichever 6 I pulled out, I plugged it, put it back in the deck. And for the second card, it needs to be black. And again, for the black card, there are 13 clubs and 13 spades. And for my second probability, I'm assuming I can pick any of the 52 cards. And in a deck of 52 cards, there's 26 black cards. So the second fraction should be 26 and 52. 1 and 13 times 1. I think this comes out to 1 and 52 if you do it on your calculator for number 13. I get 1 and 26. Oh, so much for doing math in my head. Let me do this real quickly on my calculator to make sure I don't have a mistake somewhere here. So I'm going to do 4 and 52 times 26 and 52. And then math, enter, enter. It is 1 and 26. Let's look at 15, because that might be tricky. These face cards are the jacks, queens, and kings. So let me work on 15 with you. 15, I want the probability that the first card has a face, and the second card is not a face card. It's not a jack, queen, or queen, king with eyes. And I can do that by finding the probability that the first card is face times the probability that the second card is not face. Each of the denominators is going to be 52, because for this group of problems, I'm assuming I'm putting the card back that I choose from. So the denominator doesn't increment down by 1 because of the with replacement. And then for the face cards, there's going to be 12 cards that are face cards, because there's 4 jacks, 4 queens, and 4 kings, makes up a total of 12 face cards. The first fraction is going to have a 12 in the numerator because there's 12 cards in my deck that are face cards. The second card needs to be not face, and it needs to be drawn from a deck of 52 cards. For the not face cards, that's the aces through 10s that don't have pictures. There's 4 aces, 4 2s, 4 3s. If I count all the cards that I just blocked out in red right here, there's a total of 52 cards. 12 of them are face cards. I've just drawn through 40 cards. There's 10 different cards, and there's 4 of each suit. So there's going to be 40 cards in my deck that qualify for not face. So the numerator of my second fraction is going to be 40 for the 40 cards that aren't face cards in a deck of cards. And then, let me just do this real quickly. 12 and 52 times 40 and 52. I get 30 and 169 if I think I did that correctly. Should double check to make sure that I didn't just write down something, because my answer key for problem 15 has 10 and 169. Oh, and my answer key is actually wrong, so I feel nice that I just did that. I can save an answer. That is the right answer. For 17 and 18, I'll do 18 here. For 18, I want the probability that the first card is not a spade, and the second card is not a spade. And that's the same as getting a probability of a not spade first times the probability of getting a not spade second. Both the denominators are going to be 52 because I'm putting back the card that I get on my first try. And I just need to count the number of not spades. For the not spades, the cards that are not spades are the diamonds, of which there's 13, the hearts, of which there's 13, and the clubs, of which there's 13. There's 39 cards in a deck of cards that classify as not spades. I'm assuming I picked up one of these non-spades for my first card, I put it back in, and I still have all 52 cards to choose from and all 39 not spades to choose from for my second card. I believe this is going to come out to 9 and 16, but that's probably a dumb thing to just even try to do in my head. I did get 9 and 16. Assuming my answer for 17 is right, you should get 1 and 4. I'll let you do 19 and I won't do 20 just because I feel like you might have a good feel for these. For 19, I got 1 and 169 for my answer. That's what you should be trying. I'm trying to gauge by how many problems I have left and how long this video is, whether I should break it into a part 2. I kind of have like 20 problems left. Let me just stop right here and do a part 2. The part 2 might be kind of shortish, but it might be a good time for a break anyways.